Okay, I'm going to try this again. I've been trying to put together a decent video, astronomy video. So I've got some notes here, and there's about 7 sections that I've broken this down to try to keep these videos short. So I'm going to start with the vocabulary. First thing we needed to discuss is how star systems form. Most star systems are binary or even trinary systems having 1 or 2 stars. Proxima Centauri is a good example of this. I'd have to look it up. I didn't. But I'm pretty sure there's 3 stars in that system. There's Proxima A, Proxima B, and Proxima C. Where Proxima A and B orbit around their barycenter, and then Proxima C orbits around those two in a different barycenter. So our solar system is exceptional because we only have 1 star. And so the sun is the most important object in our solar system. First, being over 1,000 times the mass of Jupiter, it is the largest gravitational well in the solar system. And pretty much everything is locked to its gravity, with the exception of some of the smaller, less massive particles who have been captured by other larger bodies. And the sun also has a magnetic field that surrounds the solar system. It also produces what's called a solar wind, where there's plasma particles that are just constantly sent out from the sun in all directions and just blasting everything within the range of what we call the heliosphere and even beyond into the interstellar medium rather. Now, that magnetic field protects us from the interstellar medium, which is just a bunch of plasma, very much similar to the sun itself, only not as dense. I don't even know what the density would be, but it's really slight. But this the movement of the sun within the Milky Way galaxy causes a compression of the heliosphere such that it's kind of shaped like an egg laying on its side, with the big end being the end that is pushing against the interstellar medium as the sun moves. So, where the interstellar medium and the heliosphere meet, we call that the heliopause. It's the border between our solar system and the interstellar medium. The interstellar medium, of course, being what is between solar systems, right? So between our solar system and the Alpha Centauri system, there's a bunch of interstellar medium and other stuff. There may be rogue planets, black holes, whatever. But so The orbit, all orbits appear spherical. However, they're actually an ellipsoid. An ellipsoid is like a flattened, like if you took a beach ball and you let a little bit of air out of it, it would kind of sag and be more of an oval. Now, some of these orbits become very extreme, and so they're no longer apparently circular. Comets are a really good example of this. And there's two types of comets. There's long period comets and short period comets. And the only difference is the time it takes that comet to make an orbit around the sun. So we're going to be doing a lot of distance measuring in here. And we're going to do it in what's called an astronomical unit. An astronomical unit is 93 million miles. It's the distance from the sun to the earth. And it is a common way of measuring distances within the solar system. And we need to finally classify planets. A planet is any object that has reached what's called homeostasis, which means that it's round. It also has to have cleared its path in its orbit around the sun, and it should not orbit another body. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, they all have met this. But Pluto and some other dwarf planets we're going to talk about haven't met that. They've reached homeostasis, but they haven't actually cleared the orbit. And so we're going to get back to that. And this is going to be the end of the first video. All right. So this will be part 2. We talked about the vocabulary and the basic idea of our solar system, just basic astronomical terms. Now I want to point out here that we have 2 man-made objects. We have Voyager 1 here and Voyager 2 here. Both of these probes were launched in 1977. They had 2 different missions, but I want to kind of illustrate the fact that Voyager 1 is traveling at roughly 38,000 kilometers an hour. And Voyager 2 is roughly 35 kilometers per hour. And at those speeds, it still took them about 45 years to get to where they are. Voyager 1 is 162 astronomical units away from the sun, and Voyager 2 is 136 astronomical units. These are the 2 furthest man-made objects in the history of mankind. and they have actually left the heliosphere, having passed the heliopause in like 2020, and are now in interstellar space. And I think at least one of them is still working, and that would be Voyager 2. But I think they fixed Voyager 1. I haven't really kept up on that. But I need to explain that our solar system, what most people are familiar with, is just the standard layout to Pluto. But what they don't realize is there's an actual cloud called the Oort cloud that is theorized to be gravitationally locked to the sun, but existing at or even outside of the heliosphere's edge or the heliopause. Something like 100 astronomical units away from the sun. And the Oort cloud itself is divided into two sections, the inner cloud and the outer cloud. The Oort cloud is 20 times the size of the asteroid belt and approximately 200 times as massive. Now, the outer Oort cloud completely surrounds the solar system like a jar, right? Like a round jar. But the inner part of the Oort cloud is a disk like the rest of the equatorial plane of the solar system. There is one object that we have found, and this is Sedna right here. Sedna has a 10,000 year orbital period around the sun. At its closest, it gets about 75 astronomical units to the sun. And at its furthest point, it's about 937 astronomical units. Now, I'm going to come back to this because it's just literally insane, the distances of this. All right, if I have orbits on, so if I click on Sedna again and I zoom out, right, the sun is right here. And look at this, how this loop goes. Now notice that there are trails for other objects because we know there are other long period comets. And that's what these are. But Sedna is technically a dwarf planet because it's big enough that it's reached homeostasis and it's round. It is the furthest orbiting object that we have identified and named. There are other objects that there's currently studying. It just, it takes time. You got to get telescope time, and that's got to, everybody needs the telescopes. There's a limited number of telescopes and a lot of researchers. So Sedna is a dwarf planet, and it's red. It's even redder than Mars. And they believe that it's red like this because of the ice that's in it, right? The Oort cloud, and later we'll talk about the Kuiper belt. Their objects are mainly ice. That contrasts to the asteroid belt, whose contents are mainly rock and iron. So that's the Oort cloud. I'm going to go ahead and stop this video here. All right. This is part 3 in my astronomy series. I'm going to try to keep this to under 10 minutes. I might have to break this up, but we'll see how it goes. So we talked about the Oort cloud in the last lesson, and I had mentioned the Kuiper Belt. There's a region of objects called trans-Neptunian objects, and these objects make up what we call the Kuiper Belt. The Kuiper Belt is a disk around the 8 planets, and it is populated by 6 known dwarf planets. It's also where we get our short period comets from. Long period comets from the Oort cloud, short period comets from the Kuiper Belt. It's roughly 30 to 50 AU wide, and like the Oort cloud, it's ice. Most of the objects in it are made up of ices. Contrast that to the rock and iron of the asteroid belt. The first dwarf planet we're going to talk about is Eris. It's the most massive dwarf planet in the solar system. Its orbit ranges between 38 and 97 AU, with a mean, not a mean. All right, so remember I talked about the orbit, how its shape, it is a oval. So there's a short side of the oval and a long side of the oval. So in this orbit, the short side is 38 and the long side is 52 astronomical units, with the sun being right, not in the center, but right where those two would meet. Now, the sidereal, right, as the planet rotates and goes from one side to the other, that longitudinal axis is roughly 67 AU for Eris. It takes roughly 559 years for Eris to orbit the sun, and it has one moon named Dysnomia, right? We can zoom in here to Eris. And there we go. So we got the moon and we've got Eris. Then the second is Makemake. Its orbit is 38 to 52 AU, and its longitudinal measurement is 45 AU. takes approximately 306 years to orbit the sun. Where are you, Mac? There you are. Come on, where did you go? Oh, sorry, I clicked on the moon. That's a Mac. And this is, I haven't studied this, but it's obviously a moon of Mac. Then from Mac, we go to Haumea. Now, Haumea and Quaoar, which is, this is Quaoar, and this is Haumea. They almost have the same orbit. We come in here to Haumea, and look at that. There's Hia'aka. How do you say that again? Hia'aka. And then we have Namaka. 2 moons. But look, Haumea actually has rings. Right? That totally blows me away. I was looking at, was it this one? If I get it right. See, if I do it like this, looks like a helium atom. That's so cool. And then we gotta go to, this is Quaoar. It has 1 moon, Wiwat, and it also has rings. I mean, that just blows me away. Now, Haumea takes approximately 283 years to orbit the sun, and Quaoar takes roughly 288 years. They both are have a longitudinal axis of approximately 43 AU, and Haumea, its orbit is 39 to 51 astronomical units, and Quaoar is 41 to 45 astronomical units. The next is Orcus. Now, Orcus is interesting. Let me find him. Where are you, Orcus? I know you're here. Where are you? Come on. Let me search. Oh, that's why I can't see it. I remember. I may not be able to show this. Oh, no. There it is. So, Orcus is actually here under that Berry Center. Now, Orcus is actually a binary system. Orcus and its moon Vanth Vanth doesn't actually orbit Orcus. It orbits a point that's roughly 13% of the orbital distance. And I find that interesting. Now, Orcus is 180 degrees out of phase with Pluto, which means that even though they have the same orbital path, they're never there at the same time, because when Pluto's at its closest point to the sun, Orcus is at its furthest point from the sun. And so, because of that, Orcus is sometimes referred to as the anti Pluto, which is why it has the name it has. Orcus is the equivalent, the Roman equivalent to Pluto, who's Greek. And then we come to Pluto. Pluto has actually 5 moons, but it's actually a binary system with 5 moons orbiting, or 4 moons orbiting Pluto, but Charon and Pluto orbit around a barycenter. And I had to delete it because I couldn't find Pluto with it. All that would pop up was the barycenter. So that was Pluto, and you could see the orbits going on there. Simulation is running. Now, there's a couple of things that I missed in the vocabulary. Anything from the Oort cloud is potentially going to be called a Sednite after Sedna. Dwarf planets from the Kuiper Belt, which is where all of these are, is they're called Plutinos after Pluto. And that is the Kuiper Belt. All right. This is number 3 or part 3 in my astronomy series. Last one we talked about the Oort cloud, and I mentioned the Kuiper Belt. And so now we're going to talk about the Kuiper Belt. The Kuiper Belt consists of trans-Neptunian objects. This is where our short period comets come from, long term from the Oort cloud, short term from the Kuiper Belt. This is a flat disk along the orbital plane. It is roughly 20 astronomical units wide, starting at about 30 astronomical units and going to 50 astronomical units. The Kuiper Belt is completely within the heliosphere. It is similar to the asteroid belt, only the objects are primarily ice in the Kuiper Belt, and in the asteroid belt, they're primarily rocky and iron. The Kuiper Belt is 20 times as wide and 200 times as massive as the asteroid belt. It holds 5 of the 6 dwarf planets. Well, 4 really. Well, no, maybe it's 5 of Sedna. Sedna is a dwarf planet, and there's another one in the asteroid belt called Ceres. But right now we're just going to talk about the Plutinos, which are all the objects within the Kuiper Belt. We are going to start with Makemake, which is, where are you, Makemake? Dang it, dang it, dang it, dang it, dang it. Where the fuck? God damn it. God damn it. Mhm. All right, this is episode 3 in my astronomy series. The last video we talked about the Oort cloud. Today we're going to talk about the Kuiper belt. There's a disk of what we call trans-Neptunian objects because they are outside the orbit of Neptune. Just as the Oort cloud is the origin of long-period comets, it is believed the Kuiper belt is the origin of short-period comets. Comets like Halley's Comet, for instance. It is roughly 30. It starts roughly at 30 AU and goes all the way to 50 AU. It is 20 times the size of the asteroid belt and 200 times as massive. Contrasting the fact that the Kuiper belt is mostly objects made of ice, the asteroid belt is mostly made of rock and iron. Inside the Kuiper belt, we have 4 or 5 dwarf planets that we're going to talk about. The first one is Eris, right here. Eris has one moon, Daesonia. Let me start and we should be able to see the movement. Eris has the second longest orbit, the semi-longitudinal axis is 67 AU. The orbit ranges from 38 AU to 97 AU. Eris is the most massive dwarf planet, but not the largest. Pluto is the largest. It takes approximately 559 years for Eris to orbit the Sun. The next dwarf planet is Makemake, right here. Oh, come on. Come on, Makemake, right here. So we can zoom in to Makemake, and you can see that it has a moon. The name of the moon, they haven't named the moon yet. I messed up. Fuck. Okay, so this is the episode 3 in the series on astronomy. Last session we talked about the Oort cloud, and I mentioned the Kuiper belt. The Kuiper belt is the focus of this episode. The Kuiper belt has, what do we have here? 6 dwarf planets that we're going to talk about. The Kuiper belt is a flat disk along the orbital plane of the Sun. Once you get in to the heliosphere, objects within that tend to rotate around what we would call a planetary disk. As the solar system is being formed, slowly stuff lines up around the equatorial plane. The first trans-Neptunian object, which is what we call the objects in the Kuiper belt, is Eris. Now, the Kuiper belt starts at roughly 30 astronomical units and extends to 50 astronomical units. And it's very similar to the inner asteroid belt. The difference is the inner asteroid belt is made of rock and iron, and the Kuiper belt is mostly ice. There's some rocks and stuff, but it's mostly ice. The Kuiper belt is the origin of the short period comets like Halley's Comet, and the Oort cloud is the source and origin of our long period comets. The Kuiper belt is 20 times as wide as the asteroid belt and about 200 times as massive. Now, Eris, our first dwarf planet. Where did you go, Eris? Oh, he's over here. Is roughly, its orbit is roughly 38 astronomical units to 97 astronomical, with that semi-longitudinal distance of 67 AU. So you could probably roughly say 67 AU. Takes approximately 560 years to orbit the sun, and Eris has one moon, Dysnomia, right here. The next object is Makemake. Makemake is a Rapa Nui word. Rapa Nui. The people from Easter Island. Makemake is here. No, come on. It's here. We'll zoom in and we'll see Makemake. Now, this simulation is showing a moon, but I don't have information on a moon for Makemake. The orbit period is roughly 38 AU to 52 AU, with that longitudinal distance of 45 AU. And it takes approximately 306 years for Makemake to orbit the sun. Next is Haumea. Haumea, right here. Zoom in. Haumea has 2 moons and a ring set. The moons are Hi'iaka and Nimaka. Right? Here's Nimaka and here's Hi'iaka. Then it takes about 283 years for Haumea to orbit the sun with a orbital distance of 39 to 51 astronomical units and a longitudinal distance of 43 astronomical units. Now, Quaoar, let's get out here to Quaoar. Quaoar begins with the Q. And that's Orcus. Where are you, Quaoar? There he is. So Quaoar is also has a ring system, and it has a moon. Its orbit is roughly 41 to 45 astronomical units, with a longitudinal distance of 43 astronomical units, and it takes 288 years for it to orbit the sun. It has one moon, Weewat, right? And it has a disk system. Disk system. Then we're going to go to Orcus, which is over here. Now it says Barycenter. Dang it. Did I just... It says Barycenter because Orcus is technically a binary system. Let's see if I can get close enough that I can pick one of these things. There it is. There it is. So dang it. All right, so this is Vant. the moon, and this is Orcus, right? And they are orbiting around this barycenter. See, because they are binary pair. Orcus's orbit is roughly 30 AU to 48 U with a longitudinal distance of 40 and 245 orbit period, 245 years. Orcus does not have a ring system. Next is Pluto. Now, Orcus and Pluto are 100 degrees out of phase, meaning when Orcus is at the closest to the sun, then Pluto is the furthest, and when Pluto's the closest, Orcus is the furthest. That's why it's usually referred to as the anti-Pluto. Pluto's orbit is 29 AU to 49 AU with a longitudinal distance of 40 AU and a 247-year orbital period. It has 5 moons: Charon, Styx, Nix, Kerberos, and Hydra. We get in here, we can see these. There's Styx, and then Charon, Hydra, and Nix. Now, Pluto is technically a binary system between Pluto and Charon. So this one's got a little bit of everything. It just needs rings. And that is it for the Kuiper Belt. All right, then. This is lesson number 4 on the solar system. There are 8 planets. Remember, the definition of planet is an object that has reached homeostasis or is spheroid in shape, has cleared all of its orbital path of debris, and does not orbit another body. The planets are broken down into 2 sets. The outer are the Jovian planets and the inner planets. I don't know if there's a name for the inner planets other than like the rocky or terrestrial planets. The first planet, our first Jovian planet, is Neptune. Neptune is comprised 80% hydrogen, 19% helium, roughly 1.5% methane. And there's trace elements. Now, Neptune is 17 times the mass of the Earth. It is the fourth largest planet by diameter. It takes 164 years for it to orbit the Earth. It's roughly 30 astronomical units from the sun, and it has 14 known planets. These aren't moving very much. What if I back out? Oh, look, there's some. Let's slow this down. Here, let's just pause it. I want this to be 1 day a second. There we go. Welcome. This is episode 4 in my series on the solar system. There are 8 planets in our solar system. Remember, the definition of planet is any object that has reached homeostasis, meaning it's spheroid in shape, has cleared its path of debris, and does not orbit an object other than the sun. So our moon, for instance, is a moon because it orbits the Earth. Earth is a planet because it's round and it's cleared its debris field, which is when the solar system formed, there was a planetary disk like this around the sun, and everything kind of coalesced together, with the first planet forming being Jupiter, and that's important for some other stuff we'll get to. Solar system is broken down by the 4 inner terrestrial planets and the 4 outer gas giants, also referred to as the Jovian planets. The first of which is Neptune, which we were looking at. Neptune is 17 times the mass of the Earth. It is the 4th largest planet by diameter. It takes 164 years to orbit the sun. It orbits at 30 astronomical units. It has 14 known moons, and it is a cyan color. This shows it as more of a dark blue, but it's actually more of a cyan. The reason why Neptune comes across as dark blue and Uranus comes off as cyan, even though Neptune is 80% helium and 19% or 80% hydrogen and 19% helium, and Uranus is roughly 80% hydrogen and 19% helium, is the fact that Neptune has these storms. And so when they took the picture, they enhanced the color and made it darker so they could see the storms on the planet. But it looks the same exact color as Uranus, which is our next planet. Uranus is 14.5 times the mass of the Earth. It is the smallest of the gas giants. Its third largest planet. It takes 84 years to orbit the sun, and it does so at 19 astronomical units. There are 27 known moons on Uranus, and it has a ring system. Let's rotate it so we can see the color. And so this is in a very good reputation. This is closer to the color. So that takes us to Saturn. Saturn is most known for its ring system, which you can see there. Saturn is 95 times the mass of the Earth. It is 90% hydrogen, 3% helium, and it is the second most massive planet. Takes 29 years to orbit the sun, doing so at 9 astronomical units, and it has 146 known moons, but technically they're impossible to count. As you can see, as I roll through here, that little dot, this little round thing, that's picking up all these dust particles and stuff that aren't even in the ring system of Saturn. Finally, this brings us to the last Jovian planet, Jupiter. I'll go in here and zoom in on Jupiter. Now, this isn't showing it, but I can add it. And there's Jupiter's rings. Jupiter is 2.5 times as massive as all the other planets in solar system mass combined. It's 1/1000th the mass of the sun. It is the most massive planet at 317 times the mass of the Earth. It takes approximately 12 years to orbit the sun, doing so at 5 astronomical units. It has 95 known moons, and Jupiter was the first planet to form. When our solar system was forming, it was trying to form a binary star system. And Jupiter formed first and started to merge towards the sun. But as Saturn and Uranus and Neptune started to form, they pulled Jupiter back out to its current orbit. It's believed that when Jupiter started, it started at a roughly 3 astronomical units, which is roughly where the asteroid belt is. And that's it for the Jovian planets. All right. This is episode 5 in my series on the solar system. We've covered the Oort cloud, the Kuiper belt, and the Jovian planets. Now we're going to discuss the asteroid belt and the inner planets. So this area here with all of these whatevers is the asteroid belt. The asteroid belt is an analog to the Kuiper belt, wherein the only difference being the composition of the material. But there are plenty of objects that have been identified in the asteroid belt, the most prominent being Ceres. Ceres is a little bit smaller than Pluto. It is the only dwarf planet that has been named in the asteroid belt at this time. The rest of these are just asteroids, maybe called planetesimals. Trans-Neptunian objects are sometimes referred to as Plutinos. And long-period comets like Sedna and other dwarf planets in that kind of orbit are referred to as Sednites. Sedna is not actually a comet; it's an actual planet, dwarf planet. But we come in from Sirius in the asteroid belt to Mars. Pretty much, Mars is a pretty well-known, I think, for most people. It has two moons, Deimos and Phobos. I'm not sure where Phobos is at this time. It might not be on here for some reason. Oh, wait, is that it? Nope, that's Deimos. All right, let's try this. Come on, man. I understand why there's lag. But Mars is approximately 0.8 the mass of the Earth, or basically 80%. There they are. Now we can get rid of one of these Deimoses. Did I catch it? No. Pause the simulation. Grab one of these Deimoses here. Oh, dang it. It is called the red planet. However, Sedna is actually redder than Mars. It takes roughly 1.8 years to orbit the sun, doing so at 1.5 astronomical units. And 2 moons, Deimos and Phobos. And then that brings us into the Earth. Pretty much everybody knows the Earth. We've got 1 moon or 1 astronomical unit from the sun, which takes 1 year to rotate. The thing about the Earth that I want to bring up again is that, we've been told our whole life, in my opinion, that what makes the Earth special is it's blue because it has water. But that blue water is actually toxic to a lot of the life on the planet. What really makes us exceptional is that our planet has green life on it. That's what makes it special. There's abundant water in the solar system, the Milky Way, and the universe, mostly as ice, but in planets like Neptune, where it's really hot because of geothermal activity in the core of the planet, there could be life. We have life like that in the Marianas Trench and stuff like that on Earth. So there could be life out there. It wouldn't be human life. It'd be microbial, but there's probably life out there. Then we have Venus. Venus is considered the Earth's twin, but it's really more of a twin of Mercury. It's roughly 80% the mass of the Earth. It's about 3/4 of an AU from the sun. Takes roughly 224 days to orbit the sun. It has no moons, but it has a massive greenhouse cloud set, which is what gives it this yellow appearance, because of the volcanic activity. There's a lot of sulfur in the atmosphere. And then finally, we have Mercury, the first of the planets, but the last in our discussion. It takes Mercury 88 days to orbit the sun. It's roughly twice the size of Pluto at 3,000 some kilometers wide. It's 0.05 the mass of the Earth. It's half an astronomical unit from the sun. And because it has this dense iron core, it is the same density rather, of Mars. So I want to show this red and green and blue. This is called the habitable zone. Every star has a habitable zone. As you can see, the Earth is right on the edge, and Venus is right in the center, and Mercury is just a little too close, and Mars is just a little bit too far. And that's it for now, folks. Let's do one quick flyby. All right, let's view, reset, and there's the Voyager spacecrafts, Sedna and Eris, and into the Kuiper Belt. Right here, look at all that debris. We fly Pluto, Neptune, Uranus, Saturn, Jupiter. This is the asteroid belt. This out here is the Kuiper Belt. And we come into Mars, and then the Earth, and then Venus and Mercury. Let's go ahead and zoom in here on Saturn and look at what Saturn's got going on. Let's turn these trails off. That's it. Let's look at Jupiter. Look at all that. Uranus, Jupiter. Boom. Look at all of this around Jupiter. Woo. Yeah. And that is the solar system. All right. This is just going to be for fun. Let's see here. There it is. I'm going to load. First, I'm going to save what I've got over here. That's not what I want. Come on. What is it? All right. Let me save this. Let me pause this. God damn it. Come on, what the fuck? Time after I eat my sandwich. Come on. Let me eat my sandwich first. Let me eat my sandwich first. No. You want a Cheeto? Hey, hey, Mango. It's tasty. Well, don't act like you don't want it, you dipshit. You'd fucking be in a bag. Oh, maybe you got heartburn. And you're like, I'm not eating that shit ever again. No. This is episode 6 in my astronomy course on the solar system. This is all about the sun. And this will be the final episode. So, our sun is a rather common sun. I mean, there are stars that range from what we would call a brown dwarf that's a little bit larger. Well, it's not a little bit. It's like 100 times larger than Jupiter. And it's just barely able to make fusion. And it's doing it in its core but its outer layers are still gaseous like Jupiter. And so they're not very hot, and they don't have a lot of light. And then that ranges all the way up to suns that are absolutely white hot with surface temperatures of at 35,000 Kelvin. So if we look at our sun, right, it's one mass of our sun, one radius of our sun. Its density is 1.41 grams per centimeter. Surface temperature is 5,780 Kelvin. Let's say that I cut this in half. It's roughly 5,000. So we'll say 2,600, right? See the color, the color changes. Now it's more reddish. We can go down to 1,000 Kelvin. And now it's red, right? And this is what we would call a red dwarf. Now we were at 5,700 normally. That's not what I wanted, but we can do that. Now I'm going to turn the volume up. Can you hear that? Well, I hope you can hear that. The sun actually makes noise, right? There's a lot of things that we don't really think about, but the surface of the sun is boiling. It boils, right? This plasma, which is a state of matter that's all of them at one time. It's a gas, a liquid, and a solid. And it just boils. And that boiling makes sounds. And even though the sound won't travel through the vacuum of space, if we could put a microphone up against it, it would be you could hear it boil. I'm going to stop. Let's see if I just pause this, what happens. No, that's not what I want to do. I'm going to change the rotational period to this to 0. So now the sun is not rotating. This doesn't show the boiling nature. It doesn't highlight the differences in the sun either. Let's get this back to 26. All right, so that's our sun. You know, it's a main sequence star. And it's what gives life to the earth. That and the water. We can zoom out. This is a different simulation. It's not as cluttered as mine. But I wanted to give one more zoom through. Let's see, there's other simulations here. Oh. Well, this one is a different version. This one has almost everything. Right, it's got Voyager 1, Voyager 2. But see, the weird thing is they have the moon here of Haumea, but they don't have Haumea. It's the silliest thing. But this is another view of the solar system. So that's the sun.
啊，